Hello everyone, myself Isaac NUTHAN. We are going to look into the topic Moire patterns. Moire patterns or Moire fringes are large scale interference patterns that can be produced when an opaque ruled pattern with transparent gaps is overlaid on another similar pattern. For the Moire interference pattern to appear, the patterns must not be completely identical, but rather displaced, rotated, or have slightly different pitch. In general, Moire patterns is referred to beat patterns produced between two gratings of approximately equal spacing. We see them every day. For example, in overlapping insect window screens and on interference between TV raster lines and striped materials, etc. And in digital image processing also, the problem arises routinely when scanning media prints such as newspapers and magazines or in images with periodic components whose spacing is comparable to the spacing between samples. Moire patterns can be obtained by the principle of pattern formation in plane and outplane moires. Here we can see what is in-plane Moire and out-plane Moire. In-plane Moire is measurement of in-plane deformation and strains, whereas out-plane Moire is measurement of out-plane deformations and strains. Moire patterns appear in many situations. In printing, the printed paper of dots can interfere with the image, and in television and digital photography, a pattern of an object being photographed can interfere with the shape of light sensors to generate unwanted effects. And also, Moire patterns are extremely useful to help understand basic interferometry. Here, in the figure given in the slide, it shows a Moire pattern formed by two set of parallel lines, one set inclined at an angle of 2 alpha to the another set of line. Here we can also see destructive interference and constructive interference from the figure. A dark fringe is produced when the dark lines are out of step 1/2 period, and a bright fringe is produced when the dark lines for one grating fall on top of the corresponding dark lines for the second grating. If the angle between the two gratings is increased, then the separation between the dark and bright fringes are also decreased. If gratings are not identical straight line gratings, the Moire pattern will be straight equispaced fringes. And now consider two functions describing the basic shape of the grating lens. For the fundamental frequency, f of x comma y is equal to an integer times 2 pi at the center of each bright line and is equal to integer plus 1 and half times 2 pi at the center of each dark line. Here f1 of x comma y is equal to the given equation and f2 of x comma y is equal to the given equation. Here where the b coefficients determine the profile of grating lines, and for a sinusoidal line profile it is only non-zero term. Here the following analysis shows how to calculate the Moire pattern for arbitrary gratings. And the superimposing of one pattern on the other creates a beat pattern that has frequencies not present in either of the original patterns. And this effect, because of this pattern of two pattern of dots, we can see this as an issue in, for example, in newspapers and other printed materials make use of so-called half-tone dots, which are black dots or ellipses whose sizes and various joining schemes are used in simulating of gray tones. As a rule, the following numbers are typical. For example, like newspapers are printed using 75 half-tone dots per inch, and magazines use 133 dpi, and high-quality brochures use 175 dpi. We see this in many places because of this two pattern of dots effect. And here, in the given figure, we can show three different Moire patterns, and in this, from A we can see the same pitch tilted with respect to one another, and in the second one there is no tilt, and we can see that the different frequencies are there, and in the third pic which is slightly tilted, different frequencies are there with respect to one another, and the equation of this is given below. Uh, these fringes are equally spaced vertical lines parallel to y-axis. For the more general case where the two gratings have different line spacings and the angle between the gratings is non-zero, the equation of Moyer fringes will be this: m lambda dash is equal to lambda dash by lambda bit into x cos alpha plus 2y sin alpha. Here alpha is the angle between the gratings, and X and Y are given. Now let us see the analysis of Moire pattern. The gratings G1 and G2 are described by the set of two equations respectively. Consider the equations as y cos theta by 2 is equal to x sin theta plus np and y cos theta by 2 is equal to minus x sin theta plus mp. The geometrical loci of all point interaction of two gratings from an array of bright fringe whose index is given by L is equal to m minus n, where L is equal to 0, 0 comma plus or minus 2 comma plus or minus 2, so on. And here L is given by 2x sin theta by 2 by p, and x is given by lp by 2 sin theta by 2. For small value of theta, we let us consider the sin theta is equal to theta. And in optical metrology, x is almost like x is equal to lp by theta, because when we consider sin theta is equal to theta from the above equation, x is equal to lp by 2 sin theta by 2, we get x is equal to lp by theta. Namely, this equation represents a set of straight lines perpendicular to the x-axis whose spacing is theta inverse times the pitch, the original gratings. Let us see the illustration of the following images. In the figure 4.19 of A shows a 1024 into 1024 zoomed image generated by pixel replication from a 256 into 256 section out of the center of the image in previous figure of 4.18. Here, let once note the blocky edges. The zoomed out image in figure 4.19b was generated from the same 256 into 256 section of the previous image, but using bilinear interpolation. The edges in this result are considerably smoother. For example, the edges of the bottleneck and the large checkerboard squares are not nearly as blocky in B as they are in A. For example, like now consider the image 4.19a. The edges of the bottleneck and large checkboard squares are not nearly as blocky in B when compared to A. And in this figure of 4.20, it shows the Moyer effect using ink drawings that have not been digitalized. Separately, the patterns are clear and void of interference. However, superimposing of one pattern on the other creates a beat pattern that has frequencies not present in either of the original patterns. Here we can see an example of Moyer effect. These are ink drawings, they are not digitalized patterns. Superimposing of one pattern on the other is equivalent mathematically to multiplying of patterns. In particularly, the Moyer effect produced by two patterns of dots, as this is the effect of interest of the following. And in the last figure, figure 4.21, it is a newspaper image of size 246 into 168 pixels. In this image, it shows what happens when a newspaper image is sampled at 75 dpa. The sampling lattice, which is oriented vertically and horizontally, and dot patterns on the newspaper image oriented at plus or minus 45 degrees, interact to create a uniform Moyer pattern that makes the image look blotchy. We discussed a technique in the previous section for reducing Moyer interference pattern. Here, the image is sampled at 75 dpa so that the image will look blotchy. That's all about Moyer patterns. Thank you.